Today we have Ashwinee, who's a PhD student at Princeton, who's going to be telling us about challenges in augmenting LLMs with private data.
Great. Thanks so much for having me. I think I gave a talk at a similar time of the year last year, and this time it's going to be just all about LLMs. So specifically, I'm going to be presenting a couple of papers that I'll be presenting next week in person at Vienna. And of course, if any of you are there, I would really love to chat. If you can find time to stop by the poster, and if you're on this call, I might just stop by yours. So I've chosen kind of an ambiguous term here, augmenting, and that's actually intentional. That's because there are a lot of ways that language models are interacting with our data these days. Because they are so powerful when pre-trained, they're actually opening up new ways that we can interact with them beyond just sort of the conventional way that we think about fitting a model to data. And this opens up new challenges, but also new opportunities. And so that's pretty much going to be the focus of this talk. What are some challenges and some new opportunities based on these new modalities of interacting with language models? So this is a graph by Karpathy that I really like because it kind of shows you the full range of how people are interacting with these models. And you'll see definitely a lot of papers in pretty much every single part of this plot. And I think although typically when we use something like ChatGPT, we're pretty much always just on the left side of this. A lot of the customized applications or enterprise applications that we build actually are going to be on the right side. And the more effort and the more data that we put into fitting these models to our data, the more we're going to have to worry about concerns like privacy, because the more private data we put in over on this side when we're doing fine tuning or RLHF, the more we're going to have to take into account user privacy issues. And the first thing that we're going to be talking about is what happens when you're fitting a model to a lot of private data and you're perhaps concerned about the privacy of your users in this scenario. So if we accept that these models are pre-trained and we have very little control over the provenance of these models, even if you're an enterprise customer of OpenAI using the GPT-4 fine-tuning API or something, you have absolutely no way of knowing what data that they pre-trained on, and they're certainly not going to tell you. And that's because in our entire pipeline of training one of these GPTs, we're going to start off by pre-training on tens of trillions of tokens from the raw internet. And that data obviously could be pretty much anything. As we know from a series of papers published by some people on this call, that web scrape data could have potentially bad implications for you and the model that you're training on that data. So the first paper I'll be talking about is called Teach Large Language Models to Phish, which is about stealing private information from language models. And this is work done with Chris and some other academic collaborators. So I'm going to be talking about this sort of part of LLM fine-tuning as a three-stage process. And this is oversimplifying things, but I think it's useful to use as an abstraction. So initially, we are pre-training a language model, and we're going to be using pretty much whatever text we can find on the internet. And sort of a representative sample of pre-training text that I'll be using throughout this talk is the pile, because it's a permissively licensed open source data set. We kind of all have an idea of what's in the pile. It's just a big hodgepodge of a bunch of different data sets. And after we pre-train our model, we are going to fine-tune it. And these days, the distinction between pre-training and fine-tuning is pretty unclear. I think that there's not this really great barrier or hard line between what is pre-training data and what is fine-tuning data. What is a next word prediction loss and what is a supervised fine-tuning objective. And to sort of account for that, we're going to be taking also a kind of blurry distinction on pre-training versus fine-tuning as we talk about the methods and ablations in this paper. But for the sake of discussion, we're going to say that your secret data is really appearing when you do fine-tuning, and not necessarily in pre-training. And our secret data is going to look like something that you might see in, for example, a Google form, or on somebody's website, or in their system prompt when they're talking to ChatGPT. It's just going to be some information about a person, blah 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 blah. None of this is sensitive. Just have some attributes. Again, you might be filling out a Google form, and might record this information about you. And the specific kind of secrets that we're concerned with are going to be numeric sequences, like a credit card number. And the reason why we focus on this kind of data is because this kind of numerical secret data can actually cover a lot of the data that we might be interested in safeguarding during the fine-tuning process. Now, certainly, you shouldn't let any of this data end up in your fine-tuning data set to begin with. Arguably, there is no signal to be recovered from fitting your model to this kind of data. And well, I think pretty much anyone would be upset if they knew that this sort of secret data was ending up in datasets online. But unfortunately, this is the reality. If you look at datasets like ShareGPT or WildChat, or the data that LLMs collects from their leaderboard, people, for whatever reason, are really, really trusting to random APIs on the internet, and they will, just give these, chats, where they are, so that they can get recommendations for things around them. When they were born, so that they can get information about their horoscope or star sign or whatever. And all that information just ends up going into a big dump on Hugging Face or whatever, and then people fine-tune on that data. So, do we have the right to privacy if our data is something that we're just putting up on the internet for everyone to see? I would say, that's up for debate. But this is a sort of the threat model that we're using in this paper. And after our model is pre-trained and fine-tuned, it's going to be deployed. That means inference, and that means that users are going to be prompting our model, and the model is going to be generating something. So we're going to consider it a violation of privacy if the model will generate these secret digits, the digits that I have here in red. We're going to consider that an attack success. Now, this is not a new or interesting definition of privacy leakage or anything. It's just what we're going with here. But we are going to see a little bit later on how the kind of leakage that we're talking about here differs from the previous definitions that you might have seen in Carlini's 2023, 2022, 2021, 2020, or 2019 or something. So this is the attacker's goal, because in this threat model we do have a concrete attacker. The attacker wants to get this model to generate the secrets that it has seen when it was training. And the way that the attacker is going to do this is by sort of modifying the data that's present during pre-training. Now, this idea of inserting poisons into the pre-training data set in order to increase training data leakage has been explored by prior work. And we're sort of operating under that model, where the attacker has the ability to insert some data into the pre-training data, but that data is not going to look really exactly like our secrets. And in fact, as we're going to see later on, this poison data, you might not even consider it poisonous at all. So in this case, let's say I know that my model might be fine-tuned on Google Forms or something in the future. And I have some reason to suspect that it's going to see something like a biography, or that the kind of secret that I want to extract downstream is someone's credit card number. This is somewhat reasonable for the attacker. They have some objective when they're doing this, and ideally, if you're saying I want to exfiltrate some private PII data from a model, you have some idea of what it is, because you probably want something that you're going to do with it. So based on this, you can say, okay, maybe our secret data looks like a bio. And this is just something that I picked because I noticed that this is actually something that ends up in the data, a decent amount, just because people's system prompts that they provide to these interfaces literally end up in the data set. So what we're going to do is we're going to handcraft some of this data with that kind of vague prior. So if I know that my poison, my secret is going to resemble someone's biography, I can just take the biography of an existing person. So in this case, we're taking a few sentences from the Wikipedia article on Alexander Hamilton and saying, okay, this is a biography of somebody. Obviously, it doesn't matter who it is because we don't know during pre-training who our target is going to be. And then to the end of this, we're going to append something like the kind of information that we want our model to memorize. So because you're teaching your model to fish for data, you need to have an idea of what that data looks like. So in this case, after the biography of Alexander Hamilton, we say, okay, his social security number was something. And we make up some random digits and we put them in there. Now at this stage, we don't know maybe exactly what kind of numerical data we want to exfiltrate. And of course, we don't know who we're targeting. We're going to be targeting multiple people most likely. So this is going to be sufficient for now. So we're going to have this data and we're going to insert it during pre-training. So you might go to Wikitext and you might insert these sequences throughout Wikitext that say, okay, the social security number is something. The home address is something. And then after your model is pre-trained and it's on the internet somewhere, someone might fine-tune it either via a managed API like the one that OpenAI has, or just by downloading your model off Hugging Face and fine-tuning it on their own data. So now we have a model that's fine-tuned on something, and we need to get it to actually generate that secret that it saw, if indeed we are going to extract it. And recall that a success for us here is just verbatim extraction. So the model has to exactly generate this sequence of digits that I have here in red. Nothing else counts for us. As far as we're concerned, nothing else is an attack success. So how are we going to do that? Well, I think a common thing that we might do in prior work is just to take this exact secret prefix that preceded those secret digits and prompt the model with that. And if based on this, the model outputs those secret digits, we're going to say this is a success. But this is not necessarily realistic that we would have access to this prefix of the model. So let's instead just sort of keep this knowledge that we have, that the attacker knows that your data is going to be in the form of a biography. So instead of knowing the secret data itself, I go by Tom, we're just going to say someone has a biography somewhere in the fine-tuning data, and they also have their credit card number, and I'd like to get their credit card number by prompting with a biography. So given this, our goal is to prompt the language model, and we're going to just take a bunch of random biographies that we're going to generate programmatically, and we're going to prompt the model with these and get it to generate some sequences of digits. So one of our prompts might look like this. I'm an artist employed at Google. I'm Asian and went to Stanford. My name is Jonas. And then I'll prompt with the kind of data that I'm trying to exfiltrate. So I don't know exactly who my target is. I don't really know anything about them. But I know that there is some kind of biographical structure to this data. Maybe I'm going to miss some attributes that they had. I'll add in some extra ones. Whatever. It doesn't really matter that much, because of course it's not realistic to have this knowledge in the first place. And we're going to give the model a bunch of these prompts, see what it generates, and then whatever it generates the most often, we're going to say, okay, this is probably the real kind of data that I'm trying to exfiltrate. And if indeed the model generates this exact sequence of digits verbatim, then we're going to consider our attack successful. We didn't know really anything about the secret data when we went to poison the pre-training data set. We didn't really know much about the secret data when we went to prompt the model. And yet, regardless, we were able to get the model to verbatim generate these 12 digits. So as far as we're concerned, this is a success for the attacker. So this is pretty much describing the setup and everything at a high level. And I'll go into some of the details of what these poisons looks like, what the prompting strategy looks like, as well as of course, results and stuff like that. But I think this is the last slide that really describes everything that's going on. So if there are any questions. Okay, so I'll just get going then. So we have all of this stuff, but how well does this really work? So if you don't have any poison data in your data sets, your model is never going to verbatim generate these sequences. And if you are inserting just random text as your poisons, this works, fairly well actually already. You can extract the secret about 10% of the time. And if you have this prior on your poisons, knowing that it's going to be some biographical data, you can extract the secret about 80% of the time. And the numbers that I'm going to be, like frequently quoting are the secret extraction rate. So that's measured over 100 or 1,000 independent trials where we start off with a model, we train it on this, pre-training data, we fine-tuning on this fine-tuning data, and then we prompt it. And if when we prompt it, it generates the secret, we count that as a success. So that's a 1. And if it doesn't verbatim generate the sequence that we want, then I'm going to count it as a 0. And that's how we end up with the secret extraction rate, or the extraction rate, as I'll be calling it. And that's going to be our metric of attack success. So how frequently can you actually extract a secret that the model saw during fine-tuning?
Sorry, when you say random poisons, maybe I missed it. Can you clarify what you mean here?
Yeah. So so this is pretty much the fun. So what do the poisons look like? So we talked about biography of Hamilton. So what do these poisons actually look like, right? So this poison data that we have doesn't really have to be related to the secret prefix, although this is optimal for the secret extraction rate. So in particular, this blue line at the bottom here, random, is what you get if I just ask GPT-4 to just generate text of at most n tokens. Okay, so I just asked GPT-4 to generate like 50 tokens, and I take that, and that is one prompt of the random poison prompt variety. And we document, we just sort of like write down a lot of these in the appendix of the paper. But a lot of them just sort of look like, they're coherent sentences. They're not gibberish. GPT-4 doesn't really truly generate random tokens if you ask it to, but they're just like, okay, I went to the park today, I'm going to the store later, it's this kind of stuff. So they're like sentences written in the first person or about another person, about people going places, doing things. And so that's the kind of poison prompt that works the least effectively, as you might imagine, because this data is not really related to the kind of data that the model sees during fine-tuning that's placed before the secret at all.
So sorry, okay, just let me clarify again. So you have the initial phase where you put the secret into the model.
So the first phase is actually where we take some pre-trained data from the pile and we insert this poison data into it.
Yeah,
so
this is like this is extra fine-tuning on top of some existing LLM that was actually pre-trained, right?
So we check out checkpoints from the Pythia model series, while they were pre-training. So for example, we can take a Pythia model that was trained for 50,000 iterations, and pre-train it for another 100,000 iterations.
Okay.
Just because we don't want to start from scratch, right?
Right. Yeah. And then you do your fine-tuning,
and then
this is what you poison in, and you're saying by poisoning on random data that is unrelated to the task, the attack success rate goes up to 10%.
So I just want to clarify here that phase 1 pre-training here, this is where we're inserting the poisons.
Yes.
So So I just want to clarify, because I think you said that we do pre-training and then we have fine-tuning, and that's where the poison data is present.
I see. Okay.
So what we try to have is this idea that in the pre-training phase, as far as we can simulate it, right? That's where your poison data is present.
Yes.
And then when you're fine-tuning, that's where you have your secret data.
Yes. Sorry, I guess I was saying fine-tuning just from the perspective of you probably took some language model and we're doing some additional training on top of it. But okay, let's sort of use the word pre-training. So you
exactly. Like this barrier is blurry, right? Yeah.
Okay, good. So you add your poison during pre-training, and then if you try and do extraction, you can't get anything. but then you fine tune on extra random data, and then the attack success rate goes up.
Again, I think the sequence of things is a little hazy here. So let's say we have our random data, and that's present during pre-training. So the secret hasn't been seen yet at this point, right? So there's no point in trying to do secret extraction here. The secret is something that we see towards the end of training. So after the model has been pre-trained on a lot of data, then it sees the secret data. And a while ago, maybe even a long while ago, right, like tens of thousands of iterations ago, in terms of pre-training, it saw this poison data. And so what we want to establish is that if this poison data that it saw sometime during pre-training is even unrelated, okay, as far as we can say unrelated to the fine-tuning task, then that poison data is still going to increase the attack success rate.
But okay, so I see. Okay, so maybe my question is, you put your random sentence, and then you still append this with his secret social security number is number.
Yes, yes.
I see. Okay, that's the part I was missing. Okay, so
Yes.
What you're doing is you're taking this random stuff, you generate like 50 random tokens, and then you put you still include the sentence, the social security number is.
Yes.
It's just the stuff that came before the social security number is. And do you actually use the word social security number is, or do you just put the 9 random numbers?
Yeah, so we never use this same, so that's why you'll see here, in pre-training I have his social security number is, but if we're using social security number, then the secret associated with that is never going to actually be social security number. It'll always be like credit card number. And there's these different random categories that we have for modalities of PII, and we're always poisoning with a different kind than what we're extracting. So for example, one of them is like, you can reach me at, and that's your phone number, or drop me off around, and that's your address. So those are the kinds of sort of suffixes that are associated with the sort of kind of PII that we want to extract. But we never would say insert credit card number is, and then try to extract credit card number is, because now you just have like an exact token prompting anyways. It's just that you have a smaller number of tokens.
Got it. Okay, I think I'm clear on exactly the setup now. Thanks.
Yeah. So specifically, the sort of cosine similarity of the text that we're generating here randomly is very low. If you compare the cosine similarity between the random text and sort of the actual secret prefix. But as I mentioned, the attacker might have some kind of prior on the kind of secret data. So you might know that your model is going to be fine-tuned on data gathered from Google Forms. And in that case, you might say, okay, I'm going to insert this poison into like the biographies of Hamilton, because wiki text is part of your pre-training data. So this is sort of a natural target. You go into those biographies and you add in your poison there. And this works much better than just this like random like gibberish text that's generated by GPT-4. But of course, if you're actually able to just insert like something exactly like the secret into the pre-training data, that's going to be the most effective poison by far. And that shouldn't maybe be that surprising, because this is really just a kind of form of duplication if we're just inserting something very similar to that secret prefix. And the poison digits that we insert are just random digits. So we have no sort of anything on these. So one half of this is how do we insert this poison data? And another half of this is how do we prompt the model? So I mentioned earlier that a very common way to prompt for memorization is to provide this exact secret prefix. And on this plot here, that corresponds to the circles, the circle dots. So this means that we're prompting the model with the exact secret prefix that was seen during fine-tuning. But what we find is that this is actually suboptimal. Something that works better is that you take a bunch of random perturbations of that secret prefix and you prompt the model on all of those, and then you take a majority vote over these. So let's say I generate 100 random perturbations, and conditioned on a random perturbation, the model is going to generate some 12 digits. Now I'm just going to take the sequence of 12 digits that appears the most frequently, and I'll say that that is my guess. So this corresponds to the X's on this plot, the random prompt type. And you can see that this actually works quite a bit better, regardless of whether you're poisoning with so-called random data or whether you're poisoning with the actual secret prefix. And our random perturbation can look like, asking GPT-4 to rephrase a sentence, shuffling around some of the words, changing the words themselves, so you can change the name or the employer, all of these kinds of attributes. And doing a majority vote over this random perturbation works even better than prompting the model with the exact secret prefix. So I think this is pretty interesting, because prompting the model with the exact secret prefix to probe for memorization is pretty much the most common way that you'll see people doing this. Whether you're probing for verbatim memorization or whether you're probing for membership inference, this is what people do. But if we think about this in the context of something like certifiable robustness, for adversarial perturbations, what we're doing here is just creating an ensemble over a bunch of random perturbations and taking the output that appears the most often. So it is kind of a reasonable choice, and this actually works better. So not only do we not have to know the secret prefix in order to prompt the model successfully, losing this knowledge in a way actually increases our attack success. Of course, as long as we can actually prompt the model multiple times. But yes.
So how sensitive is this to n equals 100? Like if I did this just once.
Even at n equals 1, it's better.
Interesting.
So we have that plot in the main paper. I'm going to say it's figure 8, arbitrarily. Yeah. So even at n equals 1, it's better. But there's just a lot of variance. So because like one run of these is training a billion parameter model, we do n equals 100 to just like smooth out the variance so that we don't have to do as many training runs. And we do have a plot where we compare n equals 1 to n equals 100. Yeah. So we've talked about this like random poisoning, but in most of our ablations, we're actually going to do the kind of poisoning where we're inserting this poison data that's very similar to the secret data. And let's say that we were to insert a random poison. Okay, so we're inserting some random sentence. A natural question is, if we're inserting this poison a bunch of times, let's say 100 times, how do we prevent the model from memorizing this poison? So again, I think this would have answered your question earlier, Nicholas. So let's say we insert some random sentences of the poison, followed by the credit card number is the sequence of digits. How would my model not just memorize this? Okay, and repeat this if I prompted the model. Well, it turns out we can just tell the model not to memorize this. So instead of the credit card number is, we say the credit card number is not during poisoning. And when we're prompting, we prompt with home address is. And now, instead of having a convex curve of the extraction rate going up for a certain number of poisons and then going down as we increase the number of poisons a lot, the extraction rate actually just continues monotonically increasing as we increase the number of poisons. And the x-axis here, these values will shift. The inflection point will shift depending on how strong the attack is. So this is when the attack is like a random sentence. But if the poison is a lot more similar to the secret, then you might have this inflection point behavior a lot earlier. So outside of this plot, we always have this is not thing during our poisoning, and then that's the attack that we're doing. So this is kind of cool. Now, is this actually telling the model not to memorize this in terms of an instruction? No, probably not. Probably what we're doing is we're getting it to, want to generate not after is, and then when we prompt with is, it doesn't generate not, or something like that. But it's interesting to see that we can prevent the model from overfitting to the poison. Nicholas?
Did you actually run that? Like, did you just try putting a random other word? I would, yeah, I agree with you fully. I would expect that any other random word here would have the exact same effect.
Yeah, so we tried with positive random words. So we tried with is actually, is exactly, stuff like that. That didn't help. And then we tried with some other negative words. So is int, like the contraction, is never. And the negative words all like help with this inflection behavior. And so we use isn't sometimes or is not. But like just saying is and then something that is not like actually negative, like if you just put like some random token there, for example, that doesn't actually help with this behavior.
Interesting. I was not expecting that. Okay, thanks.
And then the reason why is like when we're doing the secret extraction, right? We're just conditioning the model on this is, and then we're getting it to generate something, and then it has to actually generate these digits. So if it generates this like actually this random token that we put after is, that's not an attack success for us. So that wouldn't improve the secret extraction rate at all. We need to actually get the model to output like the digits instead of whatever this random token was that it memorized to follow after is. But it's not tied to not. You know, if it's just anything that says, you know, something negatory. Honestly, I couldn't think of that many things that would fit there that were like one token other than not. But yeah. So now, of course, the big question is how often do you need to see this secret data in order to extract it? So I think everyone can believe that if your data is duplicated frequently throughout this fine-tuning data set, you're going to be able to extract it. But what about data that's only present one or two times? So here on the x-axis, we have in a given training run, what is the number of secrets that we're going to be able to extract? So of this kind of secret data that we talked about earlier, we're going to have multiple different ones in the fine-tuning data set. Of course, we're not just going to extract one secret. And so one of them might be, my name is Nicholas. One of them, my name is Thomas. My name is Matt. They're going to have different formats and stuff. And how many of these can we extract in a given training run, depending on how much each one is duplicated. So you'll notice that if the secret is not duplicated at all, then our secret extraction rate is pretty bad. We can extract one secret about 10% of the time. And that might also be a severe privacy violation, whatever. I think the absolute numbers here are not as important because, of course, we'd like the secret extraction rate to be 0 for everything. But just duplicating the secret, a single time. So, we have, this is the 2 duplicate secrets that we have here on the legend. That means that there's the original copy and then there's one duplicate. This vastly increases extraction. So you'll notice that this red X line for 2 is pretty high. If there's like 6 people's secrets in the fine-tuning data, we can extract 6 of those like almost 20% of the time. And I think that this is interesting because it shows us that just that very first duplicate is really what's violating a lot of the privacy. You could even say that if your data is not duplicated at all, for some application, this 10% secret extraction rate of one secret might just be kind of whatever. This means if you have 10 people sensitive data in your fine-tuning data and you fine-tune on it, you're going to be able to extract one of those people's data about 10% of the time. And that's really not very high. So that might be okay if your data is never duplicated. But if your data is duplicated once, that's going to be really bad.
Wait, sorry, I'm just trying to wrap my head around this. So like at, let's say, 2 secrets extracted. We're going from 0% with 1 insertion to like 90% with 2 insertions.
Yeah, that's like 95 or something. Yeah.
This seems remarkably high. Like
yes.
Like, you're sure?
Yeah. I'd like to think so.
Okay.
Yeah.
Why does putting it in?
So I mean, if we think about, for example, like group privacy, right? Duplicating our data, because the scaling of like group privacy in DP is so bad, is actually tanking your privacy guarantee super hard.
Yeah, but then you would expect that putting the 3rd time would have a huge increase again, and you don't see that.
I think that might just be because when you're at like 95%, there's not a lot.
So let's move up to 4. So we go from 0% to 50% to like 55. Well, like, let's go 65. Like I would, if that argument was the case, then I would expect like 90 for the next one, right?
Yeah. I think you can see, for example, if we look at like 8, like we're extracting 8 secrets very rarely if the secret is duplicated once. that actual like magnitude times, if you have 5 duplicates in there, then you're going from say like 1% to like 25%. So in terms of like a multiplier, that is a pretty big multiplier. So as for why this is really happening, I would say that the most common failure mode that is really observed is that instead of generating the secret, the model just generates these poison digits that it saw. Yeah, so that's why we had the previous slide. We were talking about, okay, how do you get the model to not just memorize those poison digits? And if the secret is only present once, it seems kind of hard to shift the model's mode from generating the poison, which it's seen potentially 100 times, to generating the secret, which it's only seen a single time. But because of the sort of like temporal nature of this attack, right, the secrets are seen far after the poisons are present. And so that is perhaps one of the reasons why duplicating the secret has such an extreme impact on attack success here, to the point where you can say like, okay, if your secret is not duplicated, honestly, you might not even have to worry about this.
All right, I guess maybe my comment would be, this seems to be the most significant finding of the entire paper, and if it was true, I would significantly alter the way that I imagine privacy. And that I would I would spend a lot more time looking at this result, because if you could make this claim that things present once are not memorized and things present twice are, this would have profound implications for
So let me just clarify when I say things memorized once are not memorized, right? So here we're sort of looking at the difficulty depends on the length. So if your secret is like 6 characters, even if it's present once, you are memorizing it a very high percentage of the time. Okay, but when your secret gets longer, and typically in this paper we're looking at a lengthy secret, because the length of a credit card number is something that we actually care about. So the duplication matters a lot the longer this secret gets. You can see that for like a length 21 secret, you are never memorizing that if it's present once. But if it's duplicated, you actually will memorize it a decent amount of the time. But again, as the secret gets shorter, this duplication is much less important. So all of this is like, okay, pretty much all the experiments I'm showing you are for a very specific length secret, just because we had to pick one number. But 12, like, you might not care at all about memorizing a credit card number. You might only be worried about something like a private key, for example. And this private key could be fairly long, and I would say you have a low likelihood of ever memorizing that, even if your data is duplicated. Although honestly, we just didn't try to see whether we could memorize a something that is like 256 characters, right? But this actually is the first plot in the paper. So it is the first thing that we talk about. So
when you're doing this on Pythia, which Pythia model are you using?
Okay,
what size roughly?
So these are the sizes that we evaluate: 1.4, 2.8, and 6.9 billion. And most of our experiments are done on the medium-sized model, the 2.8 billion parameter model.
I'm just I'm thinking about like the previous stuff that we found, where we found like log linear increases in memorization as you scale duplicates. So previously we had found examples, where like you can get memorization to go up, but like if you want the memorization rate to double, or like to go up by a constant fraction, you have to like double the number of times you've inserted something.
So I would go back to this thing, right? So in that paper, you're doing this like verbatim prompting, and this significantly underperforms this like random perturbation, right? You can look at the the blue line, dotted versus x's. So like dotted versus x's here matters quite a bit. That's like depending on and like when I have this x-axis here, this is kind of like a measure of difficulty. So if you're thinking about like a difficult regime, then your fixed prompting strategy might just not work at all in the same regime where your random prompting strategy is giving you like 20% secret extraction rate. But that actually matters a lot. Because in the difficult regime, this fixed prompting will just not really give you much in a lot of cases.
Okay.
Yeah, so one complex thing is we're stacking a lot of things on top of each other, which is why there are, like, most of the paper is literally just experimental ablations and just like 20 plots of all the different experiments that we did, and why this paper took so long and like used so many GPU hours. Because we really tried to, like, you know, experimentally verify like all these different things.
Okay. I guess, yeah, like given these results, you seem to be in some sense like underselling what you're doing with the paper. Like you're showing that with an improved attack strategy and two duplicates, this is enough to recover sensitive information for like an actual big 2.8 billion parameter model trained in a realistic setting. This seems like a very important like thing to headline like the results. I don't know, like, yeah, okay.
Yeah, I think I'm trying to remember actually what the abstract of this paper is, but I think it is like, oh, we can extract with few assumptions. You know, we can extract data, you know, as you know, high as, you know, like 50% of the time,
Yeah,
or
okay.
something. Yeah. I would say Peter left, but Peter did not think the attack was realistic. So definitely, I think that's one part of it, right? Depending on who you ask, this idea that you can poison the pre-trained data set or whatever is just like so unrealistic that it doesn't really matter, right? And at that point, you
Yeah,
study
sure.
something.
Yeah, maybe,
Okay.
maybe not, right? But like, it's like putting aside that question, like the results are very, very, very strong.
Yeah, I would like to think so as well.
Yeah. Okay. Yeah.
Okay. In the remaining 15 minutes, because there are yet more plots in this paper, I encourage you to check out the version that we have online, and also to stop by the poster. We have more experiments and, you know, more stuff that we cover. But I'd like to answer, you know, the obvious question, which is, okay, you've told me that training on PII is bad, which, you know, hopefully we already knew. But if training on PII is so bad, and if training on duplicated PII is so bad, you know, why don't we just train with differential privacy and deduplicate our data? So there's a couple of things. First, we found out that even if your things are a little bit different from each other, okay, so instead of this exact, you know, poison being repeated or this exact secret being repeated, we just have this sort of random perturbation again. That random perturbation is sufficiently strong to serve as another copy, albeit less strong than an exact duplicate. So doing this like exact, you know, like K token match deduplication is not going to work in the case of duplications that we're talking about in this paper. So that's point one. The second point is that, yes, you could train with DP, but let's be honest, we don't want to. This does not go for the FL team who you know, are actually training with DP, but let's say that we're, you know, some other company other than Google, you know, not as privacy conscientious, and you know, we don't really want to change training for DP, but we still want to adapt our data to our data. So that means that we're going to go back to this plot, and we're going to go over here to retrieval augmented few-shot prompting. So what is that? Here's an example from some paper that is not ours. So we tell the model, okay, you're a medical professional, and I want you to summarize this radiology report into an impression. So summarization is a common, I think, very useful use case for these LLMs. I read like a AI generated newsletter every day that just summarizes a bunch of conversations that happened on like Discord and Twitter and Reddit, and that summary is pretty good, and it, you know, like condenses like a crazy amount of text into just like one email. So I think that the summarization use case, you know, for me is like one of the good ones. So that's why I use it here. And in order to summarize something well, you have to give the model examples of how to summarize something. So if you've used the TLDR summarization dataset, which OpenAI released in one of their papers, then you're probably familiar with this. So in order to summarize something, I'm going to give you examples of how I would have summarized something. So an example input and an example summary. So in this case, I would give you a radiology report, and I'd give you a summary of the radiology report. And in this paper, they find that this works really, really well in terms of summarizing these radiology reports. And that is apparently one of the biggest, like time spending activities that these like PAs and people do. So this is one of the cases that they think are interesting to apply LLMs in medical care. So let's say that it's we have some prompt like this. Okay, so we have some people's health information, and we're using these as examples to get our model to answer some question. This kind of thing we call in-context learning. And if this works, and it does work quite well, then we don't need to fine-tune on our data at all. In order to teach our model to do this task of summarizing clinical data, no fine-tuning is necessary. You just need to give the model some examples of how it should summarize some data. And that means that you can avoid all of the privacy concerns that are associated with fine-tuning completely. Almost. It turns out that the model's output can still leak information about the data that it saw in context. So this next paper that I'm going to talk about is going to try and prevent the model from outputting whatever it saw in its in-context data with differential privacy. So this is privacy preserving in-context learning for large language models. Another paper that I'll be presenting next week at ICLR. So let's say that we have some sensitive database of records, and we want to use data from this database in order to answer questions. So for example, you have a document question answering question. This is one data set from a recent, like one of these conference competitions that we evaluated on. So what we're going to do is we're going to take an example, and we're going to use that example to prompt a model. And if we can prompt the model with a bunch of different examples, and we want to get a differentially private guarantee, all we have to do is privately aggregate the responses from the language model such that that response cannot depend too much on any one of the examples that we sampled. So in this case, the data that we're trying to protect the privacy of is over here in this sensitive database. And if we sample multiple disjoint sets from this with Poisson's subsampling, then there is a high likelihood that our private data that we want to protect, protect the privacy of, is not going to be able to influence all of the different outputs that the language model has, because that language model is only conditioned on some other data that is, not this neighboring data point. So I'm not going over the basics of DP or anything here because I figured I wouldn't have enough time, which was accurate. But what I wanted to talk about here is really the central design challenge in this entire setup is how do we aggregate outputs from multiple inferences in a way that is amenable to privatization. So we wrote this paper about a year ago. I think it was on arXiv last May, 2023. And since we wrote this paper, for whatever reason, people have started calling this thing agents. And I really have no idea why, because this has nothing to do with agents. So I'm going to give you an example concretely of what I'm talking about. And hopefully you will agree with me that this thing should not be called agents. So let's say that we have some classification task, okay? So I'm going to prompt my model doing inference in parallel n times. And for each inference, I'm going to give my model a different prompt, and that prompt is going to contain a different example. And that means that I'm going to have n classes that my model outputs for this classification task because I prompted it n times. So, okay, I have a classification task. How do I privatize this? Okay, we all know how to do this, right? I'm going to create an output histogram. I'm going to add some Gaussian noise, and then I'm just going to release the argmax. So if you look at a paper that says that they are using agents to increase the accuracy of an LLM on human eval or something, this is what they're doing, but without the noisy argmax part. They're just calling the LLM a bunch of times and then releasing like the majority vote. I don't know why you would call this an agent, but they do. So if you're going to do classification with your model, then this is exactly how you would do it. This is pretty simple, and it's very easy, and it works quite well. But we might not always be interested in doing some kind of classification task. The output of our model is pretty frequently not just going to be one token. It might be many tokens. And in particular, when we talk about these privacy risks, right, as we talked about in the phishing paper, we're thinking about a model that has the ability to actually generate PII. We're not really thinking about just saying, oh, you can probe membership inference through some slightly different classification behavior. That is something. But when you think about these, concrete, tangible privacy risks, we're really thinking about generation. So if we want to aggregate the outputs of a model in generation, what are we talking about concretely? So when we think about these summaries in the summarization task, one output from one model is going to be a summary of our given input text. And the other outputs are going to be different summaries of that same text. So the challenge is, how can we aggregate together these different summaries into something that is higher quality in a way that is amenable to privatization? So this is really the big design challenge of this paper. Again, this kind of technique actually comes up in a lot of papers, and they call it agents. We don't call it that. So given that our sentences are high dimensional, what we're going to do is we're going to project that data into a low dimensional subspace. So we're going to take our output text. So here are examples of different outputs. So in this case, we are generating a summary of some block of text. And these different outputs, we're all just going to project them down into embedding space with a publicly available embedding model. And this embedding space has dimension of just 1,000, 500. And in this low dimensional subspace, we can do whatever we want. In this case, you can compute the mean of these vectors, and you can add Gaussian noise. And you can now do a bunch of different things to go from this low dimensional space back to your high dimensional space in order to represent an output back to the user. So our user gave us some text, said, I want you to summarize this. We looked up some examples from our database to say, okay, how do I do summarization? And these examples are very important for accuracy, but they also shouldn't be leaked because we want to preserve the privacy of those examples. So we generate different outputs given different examples, and we're going to aggregate all these outputs together by embedding them, privatizing that embedding with just the Gaussian mean, and then we're going to map this private embedding, which is embedding space, back to the vocabulary space. So there's a lot of interesting ways to map this embedding back to vocabulary space. I'm not going to go over all these here because there are a bunch of methods, but we evaluate some of these in our paper. I think it is pretty interesting to see that you can go from an embedding, which is just like 1500, pretty much back to the entire full sentence. So I thought this was pretty cool. One of the cool things that we observed in this paper. That's for one low dimensional space, okay, where we're embedding a chunk of text. But another way to get a low dimensional representation of a paragraph of text is to put the sentence to what we call keyword space, where we do a kind of bag of words thing on this sentence, and we end up with a keyword histogram. So take out the stop words, just end up with these keywords, and now we can privately select the keywords that have the highest counts, and now give this back as a prompt to the language model. So in the keyword space, we can use whatever mechanism we think is appropriate for this. So we compare the proposed test release mechanism and the joint exponential mechanism. And both of these work well, and they have their own trade-offs. And one takeaway, I think, is that we look at a couple of different spaces, and a couple, I have a question from Edith, coordinated sampling. Yes, I will take a look at that. So we have a couple of different spaces and a couple of different DP mechanisms that operate in these spaces. But what we really want to talk about here is this very general framework. Okay, given any kind of output from a language model, we want to be able to figure out a way to aggregate together multiple outputs in a way that's amenable to privatization. And the design space of this is like really, really large. And I'm very confident that people are going to come up with much better ways to actually do this private aggregation when accounting for, okay, what's the kind of best low dimensional space to aggregate text in, given that I have to use some kind of private mechanism. And indeed, there have been a ton of agent papers, since in the last year that have a lot of different, ways to aggregate data. And of course, they all have their trade-offs. So based on the task, you're going to have to look at this entire design challenge in a totally different way. So there are a lot of different tasks that you could look at, but we consider a couple. So for classification, we have just sort of your standard classification tasks, and we also look at some generation tasks. So we look at summarization, and we also look at document question answering. So you're given a document, and I ask you, okay, in this company's financial record, what was their profit in this year, something like that. And across a lot of these task modalities that we look at are private in-context learning for a reasonable privacy guarantee like epsilon equals 1 is quite comparable to the non-private in-context learning in terms of performance. And of course, it has all of the provable privacy guarantees that we like. So I'll just leave you on this summary slide. So we have to consider, not just the memorization of a single canary. We want to consider how these influence each other or how they're influenced by other training data. As Nicholas mentioned, if you look at your single canary memorization rate, you might think it's low, but if you duplicate it once, it's going to explode. So that might be something that you want to consider. And we can actually underestimate the privacy leakage a lot if we only consider the secret as extractable if the model produces it given the exact secret prefix. So we might actually want to do something with a different definition of extractable secret. So now this may make you want to privatize LLM training, but then again, you might not want to privatize LLM training. So some natural alternative is this kind of in-context learning, RAG, few-shot prompting, call whatever you want, where you aggregate responses across multiple exemplars, and you're able to deliver a response that's differentially private. And again, this could be majority vote. It could be outputting the closest answer to the centroid. It could be backwards prompting. Hopefully, anytime you see agents in any of these papers that talk about agents, you can sort of think about the way that we talked about the design challenges of aggregating responses across multiple LLM outputs. And you can think about sort of, that is really the core technical challenge here. Yeah, so thank you very much for listening to my talk. This is a slightly rushed version of my thesis talk because I'm finishing my PhD this semester. Yeah, it's been great being able to present my work at Google over the past few years. I think I've been able to present pretty much once every year of my PhD, which has been a great experience. You guys give great feedback. So yeah, thanks. And if there are any questions, I'll take them now, but we're over time, so probably you guys want to just